Welcome back. This is part 4 of chapter 3. This is our last recording for chapter 3. We're again going to pick up where we left off. We were talking about the chi-square analysis and critical values. Now let's go back and compare Mendel's experiment with de Vries's experiment. Okay, so when we calculated Mendel's chi-square statistic for his dihybrid crosses, we found that the value was 0.51. Now remember, we're doing a dihybrid cross. 4 phenotypic outcomes. Our degree of freedom is going to be 3 because it's 4 minus 1 is 3. So what we're looking at is this 5% critical value, okay, 7.815, because we're looking at 3 degrees of freedom here. Now because 0.15 is much less, 0.51 is much less than 7.815, we are definitely supporting this hypothesis. So Mendel's data does support his hypothesis. However, for de Vries, okay, again, a dihybrid cross, so again, the same degree of freedom, 3 degrees of freedom. We're looking at 7.815 as our 5% critical value. 22.94 is his chi-square statistic, obviously much greater than 7.815. We're going to reject that hypothesis. So his results do not support his hypothesis. Okay, now onto the last part of the chapter, Mendelian Principles in Human Genetics. Now we can do some analysis of human genetics, but it is a little bit difficult for obvious reasons. Obviously, we can't perform controlled crosses like Mendel could. We don't always have complete family records, and as humans, we don't have a ton of progeny, a ton of offspring. However, even with this, we are able to see a lot of different inherited conditions in humans. So this table is showing you different disease conditions, but even normal traits that are passed on from parent to offspring, such as eye color or hair color, things like that. We can analyze in human, despite the fact that it's a little bit more difficult. Okay, so the one way that we do this, one way that we follow genetic traits in humans is by using something called a pedigree. Now, a pedigree is a very simple way to represent the relationships within a family. So here are just some pedigree conventions. Males are always designated by squares, females are circles. If you have the trait that is being analyzed by the pedigree, it's a filled-in shape. Deceased individuals have slanted lines through them. And we're looking at different generations. So we use Roman numerals to designate different generations. So the parental generation will be 1, and their children will be 2. If you have individuals joined by a horizontal line, such as this one, that indicates a mating. All right, so if we're looking at whether or not a trait is dominant or recessive in a pedigree, looking at human genetics, it's very easy to look at or to recognize a dominant trait. For one, every individual who carries the dominant allele will show the phenotype, and we know that already. Each individual with the phenotype will have at least one parent with the phenotype, and that makes sense because, so for example, this individual here, okay, so this father has 2 children with whatever trait that this is referring to. Now, obviously, this parent must have the dominant allele in order to have the condition, and so he would have passed on that dominant allele onto this child and this child, and then this child passed on to here, this child passed on to this one, this child passed on to this one, and so on and so on. And here we have a pedigree of 5 generations. However, if that dominant trait is going to be associated with reduced viability, so early death or reduced fertility, then you're going to end up with a rare phenotype. Most individuals are going to be heterozygous because if they were homozygous, that's going to be associated with more of a reduced viability or fertility, and you might expect that half of the offspring will inherit that condition. That's sort of a caveat to dominant inheritance. All right, if we're looking at inheritance of a recessive trait, obviously they're going to be more rare, okay? And the individuals who do have that trait, okay, they're going to have parents who do not show the phenotype, typically. Okay, and these rare recessive traits are more likely and families with parents who are related to each other. So, for example, if you have first cousins who have children together. All right, so let's look at some other Mendelian segregation in human families, some other ideas here. Now, again, because humans have a small number of offspring, we do not have the power of the large number of offspring, those numbers that Mendel had. So what's going to happen is that our phenotypic ratios that we're going to see in these human families are really going to deviate from what we expect in the Mendelian ratios, and that is simply because of numbers. And this is a good illustration as to why it's really important for, when anyone is doing any kind of experiment, to keep doing the experiment over and over to really and have a lot of experimental subjects so that we get a lot of data, a lot of numbers. All right, so moving on to genetic counseling. So sometimes people are worried, well, if they have a particular condition that runs in their family, what's the risk that it's going to be passed on to their offspring? Now, a genetics counselor is someone who assesses the risk of the prospective parents and explains it to them. So your book gives you a couple of examples of what the genetic counselor might be faced with. So, for example, a recessive condition, autosomal recessive condition of cystic fibrosis. So suppose you have two heterozygous parents, and we can think about, what's their risk of having a child with this particular disorder. So we can think about, well, how many of their children are going to be unaffected and how many are going to be affected. Now, in this case, there's two possible phenotypes. Well, they're either going to be affected or they're not, right? So that's referred to as a binomial probability. Your book defines that in this chapter. So what we want to do is calculate the probability of each possible outcome. So the easiest ones are, well, if we have 4 unaffected or 4 affected, okay? The possibility of 4 unaffected, now keeping in mind this is a monohybrid cross between 2 heterozygous individuals. We know back from Mendel's monohybrid crosses that there's going to be a 3 out of 4 chance that the offspring are going to have the dominant phenotype, which is the unaffected phenotype. Okay, so it's going to be essentially, remembering our multiplicative rule, 3/4 times 3/4 times 3/4 times 3/4, or 81 over 256. The probability that they will all be affected, again, remembering back to Mendel's monohybrid crosses, the probability of the homozygous recessive condition is 1/4. So again, our multiplicative rule, 1/4 times 1/4 times 1/4 times 1/4. There's a 1 in 256 chances that all of the children are going to be affected. All right, that's the easy thing. Then we get into a little bit more difficult. If you think about whether you're going to have 3 affected, 1 unaffected, or 2 and 2, or 1 and 3, you actually have to consider random birth order. Because if you have, and your book goes into this in a lot of detail, if you have 3 unaffected and 1 affected, you could have your unaffected child first, and then 3 unaffected. You could have an unaffected child, then an affected child, then 2 unaffected children. So the birth order matters when you're determining the probability, so you'll want to look at that in your book. All right, another example, non-polypoid colorectal cancer. Here's a very large pedigree, 5 generations, showing the inheritance of this particular type of cancer. Now, this is a little more complicated. It's a dominant trait, which should be obvious to you from looking at this pedigree. The incidence is about 1 in 500 people suffer from this, but the median age of onset is 42 years old, which basically means that, in general, most people, if they inherit the allele for this condition, they're going to develop this condition by the time they're 42. So this is really an age-related question. So in this family, what you can see is that at least 1 affected individual is affected in each generation, and each affected individual has an affected parent. Now the issue arises with generation 5. What we're looking at is 7 unaffected individuals, 2 affected individuals, but of these 7 unaffected individuals, all of them have a parent who is affected. So they can definitely, they definitely have a chance that they have inherited an affected allele. But just because they're unaffected now doesn't mean they're always going to be unaffected. Okay, they could still develop the cancer later in life. So in this case, their risk is really a function of their age, and the genetics counselor would really have to determine that. Another example, albinism. This is an autosomal recessive condition. This is where there's absolutely no pigmentation of the hair, the skin, the eyes, anything like that. No pigment whatsoever. So let's take this particular pedigree. You have two parents here. You have parent R, the father, and the mother is parent S. Now the father has two brothers with albinism, but he himself is not an albino. And then the woman, parent S, she has albinism. Now because this is a recessive condition, she must be homozygous recessive. Okay? Now because he has normal pigmentation, he might still have that recessive allele that he must have gotten from one of his parents. Okay, so he could be heterozygous or he could be homozygous dominant. We don't know that. So the question is, their child, their child T, what is the risk of that child developing, being born with albinism? So there are two questions here. The first question is R a carrier? Okay, is R heterozygous? Does R even contain, or did R even inherit that recessive allele from his parent? And if so, what is the probability that he will pass that affected allele on to his child T? All right, so let's look at this. We can look at a Punnett square that could help us out. So first of all, is parent R a carrier? Not a character, a carrier. Okie dokie. All right, so R here, the parents again. These parents, each of them must be heterozygous because they were able to generate or produce homozygous recessive offspring, yet they do not carry the trait themselves. All right, so R can be either homozygous dominant or heterozygous, but he cannot be homozygous recessive because if he was, he'd have albinism. Now, if we look at the Punnett square, and we look at these two heterozygous parents, okay, so the male, the father, could only produce sperm, one that contained the autosomal, the dominant allele, one contained the recessive. Same with the female. She could only produce a gamete with either a dominant allele or a recessive. Simple Punnett square, simple monohybrid cross. Of the three normal phenotypes, okay, among them, all right, 2/3 are heterozygous. 1/3 is homozygous dominant. So he essentially has a 2/3 chance of being a heterozygous carrier. All right, now, so it's true. He does have a chance of being a carrier. If so, what's the probability that he's going to pass this trait on to his offspring? Well, if he is heterozygous, he has a 1 in 2 probability of passing that recessive allele onto his offspring. So the probability of both events happening, this is an AND situation, our multiplicative rule, 2/3 times 1/2. He has a 1/3 chance. So essentially they have a 1/3 chance of having a child with albinism. This concludes Chapter 3. I hope these were helpful to you. Join me again when we look at next week's material.